Hey guys, here's a video with an introduction to antiderivatives. So if you're looking at the document that has the examples from class, I'll just kind of go through those. So we started by trying to find this pattern of, if these are all derivatives, let me just scroll down here a little bit. If these are all derivatives, f prime of x is 1, or x squared, or x cubed, and eventually x to the n, what would the original function had to have been to end up with those derivatives? So it didn't take long to figure out, well, the first one, f of x, would have had to have been x, and we all kind of agreed on that, except I kept telling you there was a little bit more to it than that. The derivative of x, of course, is 1. This is a possible answer for the antiderivative of 1. The problem is it's not the only correct answer. So what we had to do is we had to account for the fact that there could be some constant, which we call c, that when added to x is still, still has a derivative of 1. The only difference is, whatever this graph is, a linear graph, y equals x, right, slope of 1, it could be shifted up. So if this is the actual graph, right, of y equals x, well, it could be y equals x plus 5, or it could be minus 2, or minus 1, or plus 3. It doesn't really matter. The derivative is still 1. The slope of this line is 1, whether I put it here, 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 or up here. It doesn't make a difference. So we have to account for that, and we do that by saying, by adding some constant c. And the c, of course, can be negative. It's just generally put as plus c. And that's what we call the general antiderivative. So the general antiderivative of 1 is x plus c. So if we follow that same pattern, g of x would be, well, the antiderivative of x, if I want to start, it would have to be something with x squared, but x squared has a derivative of 2x, so I have to divide out that 2 if I want to end up with just x. So it would be x squared divided by 2, again, plus the c. And these are really easy to check. Just take a quick derivative. If you take the derivative of what you think is the antiderivative, you should get back to where you started. So in this case, if we take the derivative of x squared over 2, we will get x. Okay, if we take the derivative of x squared over 2 plus c, we still get x, because the derivative of a constant, of course, is 0. All right, this pattern does continue. So if I want, let me just scroll here a little bit so you can see a little better. If I want the derivative, if I say the derivative is x squared over here, well, then I must have started with something x to the third. The problem is, again, if I take the derivative of x to the third, I have a 3 in there. This derivative does not have a 3. So I have to reverse that and divide it out. So this would be x cubed over 3 plus c. And of course, you could write 1/3 x cubed. That's the same thing. But nevertheless, we still have to have our constant c. No need to stop there. Oops. If our j prime is x cubed, then our original would be x to the 4th over 4 plus c. And then here's where it gets interesting to try to come up with the actual pattern for it. If we started with x to the n as the derivative, what was the original function k of x? And if you look at the pattern, it looks like the power always went up by 1, right? Let me scroll up again, right? We had 1 here, we ended up with an x. We had x here, we ended up with an x squared. X squared became x cubed, etc., etc. So it doesn't take long to make the connection that we have x to the n plus 1 for our power. And then what do we have to keep dividing by? That exact same power. Divide by 1, divide by 2, divide by 3, divide by 4. So divide by n plus 1. And don't forget the plus c. And that is 99% correct, with one minor exception. This pattern only works as long as the power is has a specific domain. And that domain would be all numbers except for -1. Because you can see very clearly that if n was -1, our antiderivative would have a 0 in the denominator, be undefined. There's a whole other section devoted to what happens when n is -1, and we'll get to that in a couple of chapters, actually. So for right now, we're just going to focus on when the power is anything but -1. That's the basic idea. This is, again, called the general antiderivative. All right, let's do an example using that, and if you are following along on the notes from class, this is the example we did. Let's find a general antiderivative for g prime of x. So we break it down and we say, all right, what would g of x had to have been in order for this to work? Now, the first thing you probably recognize is that all of a sudden there's a trig rule in here, but that's okay. Think of an antiderivative as what did you have to start with to end up with that derivative? So how do you end up with sine of x? Well, that would be a cosine function, but is it positive or negative? Well, take 2 seconds and take those derivatives. Cosine, the derivative is negative sine, but this is not negative, so we actually need a negative cosine x. What about the 4? Do we do divide by 4 here? Nope, this is just a constant multiple. It's kind of coming along for the ride. Again, if you're not sure, take a quick derivative. Cosine, the derivative is negative sine. Negative times negative is positive. 4 is just 4, and that's the original antiderivative here, 4 sine of x, or derivative, excuse me, 4 sine of x. Now this other part, we have to do a little work too, because I never said anything about a reverse. I never said anything about a reverse quotient rule, right? So what do we got to do? We got to break it apart. Sorry about that. Got to plug that in. We had to break it apart and then find our reverse power rules, using the general antiderivative rule that we just came up with. So let's take a second to actually rewrite this part. I'll do it up here. 2x to the 5th over x minus the square root of x is the same as 2x to the 4th minus x to the negative 1/2. If we just split that up a little bit. All right. So now my eyes are going to be focused over here as a rewrite for what was over here. So the antiderivative, if I use the pattern, is going to be 2x to the 5th over 5 minus, careful here, we still have to add 1 to the power, so that's going to become x to the positive 1/2 divided by the 1/2 for using our rule, the n+1 rule, and then plus c. Now you might ask, how come we don't do a plus c for each part? And that's a good question. We technically could, but it wouldn't be the same c. It'd be like c1, c2, c3, and if you put all those together, you get a c4, or whatever you want to call it, c, d, and e. It doesn't matter. That constant is already accounted for in here. So all the little constants that led up to each of these antiderivatives is already encompassed in this plus c here. That's why you only need to do it at the end. All right? And obviously we can clean that up a little bit. There's not much to do here. You could write it as 2/5 x to the 5th minus 2x to the 1/2. Maybe that's even written as square root of x. It's the same thing. And then, if this was a book problem, it would probably look something like this. All right, and those are the basics. I'll go ahead and make another video with the more complicated examples, but that should probably get you started. If you need any help, be sure and let me know, and I'll talk to you later.